Last time we introduced the notions of independence and of a discrete random variable, and today we are picking up on both of those notions. As far as independence is concerned, there was this slightly subtle definition that required us to say that a family of random variables is independent, and if for all finite subsets of our index set I, these probabilities of intersections are equal to product of probabilities. And we did some calculations with that, such as showing that A and B independent implies that A and B complement are independent. I wrote an extension to that last time involving infinite families of random variables. In some way, what I've written here is a special case of that. If I only have finitely many random variables, I can put complements to any subset of them, and I will retain a family of random variables that is still independent. And that's what we are going to use today when we develop a few more examples of discrete random variables, really. The other concept we introduced on Monday, no, Friday, today is Monday, sorry. Anyway, a discrete random variable. What's a discrete random variable? It's a function on a sample space, and it has to satisfy two properties. One, it takes only countably many values, and two, the sets where x takes a fixed value, little x, that is all omega in omega for which x of omega is little x, all of those sets for x real number have to be members of this set F of subsets of omega that is part of our definition of a probability space. Right? That is a kind of another one of these technical conditions, the condition in B. What you should remember is the definition of a probability mass function, that I'll abbreviate PMF, which is collecting all of those probabilities of x taking specific value little x as a function of that specific value little x. And that kind of is the way to maybe remember that condition B, that needs to be meaningful, so the event x equal to little x has to be a member of the set of events to which the probability function P assigns a probability. Right, so what I've defined here, let's look at the detail here. So I've defined the notion of a probability mass function, and I've said it is the probability mass function of x. So first there was the random variable, and then we said, well, if it's a discrete random variable, it must have a probability mass function. There is now a natural notion that we can define, which is the definition of a probability mass function without there being a priori a random variable whose probability mass function this is. So we can just look more abstractly at functions from R into R, and then we can put down some conditions here. So namely the conditions that we have up there, that essentially I being a set of x in R for which q of x is non-zero. That corresponds to our values where we want to assign a positive probability to the little x. Well, under what conditions is this a probability mass function? So we can say this is called a probability mass function. If, well, the one condition that I've made very explicit is that the sum has to be equal to 1, but there is one other condition that I have not made so explicit, which is that here I put a codomain that says it has to be non-negative as well. So let's put that explicitly into the definition of what a probability mass function is. For all x in R, we require q of x to be greater than or equal to 0, and the sum over all relevant x, namely the x in I, this is a sum over q of x's that equals 1. Okay, so here I've defined what I want to say is a probability mass function. And with that notion, of course, there are now some natural questions that you can ask, such as, is there always a random variable whose probability mass function this is? And that's kind of the question that justifies this terminology, or rather the answer, yes, justifies this terminology. And so let me not make a big meal of that, but let me say here is a remark. And the remark is that we can always define a sample space. We can just take that set of values that we assign positive probability to as our sample space. We can define P of E as the sum over all x in E of the Q of little x's for E subset of omega, and we can then say what is our random variable. We can say x of omega, where omega is now I and I is a subset of the real line. Well, that is just equal to omega, and then you can check that then the px of this random variable is equal to q. Okay? There is not much to do, but it is worthwhile just thinking through, if you so wish. But most importantly, the message here is there always is a probability space on which we can have random variables that we want to specify by their probability mass function. Okay? So that will allow me, when I extend the examples that I started last time, that will allow me to say, oh, here's a probability mass function. That's another example of a distribution. And, well, there is also a sample space and a probability function such that you can exhibit this distribution as the probability mass function of a random variable. Okay? So, yeah, I mean, the independence that I care about is still visible up there. Actually, that's what I care about independence. So if we now go on and extend a little bit our notion of distributions, classical distributions of random variables, let's pick up on the Bernoulli distribution that I introduced last time. Because the next two examples are going to involve in some way more Bernoulli variables, and it will be useful to have some terminology here that we can hook onto. So the terminology that I'd like to invoke here is to say, if I have x that is Bernoulli distributed, I can call that a Bernoulli trial. Trial as in we try several times, possibly later on, but here is a single trial at achieving something with which we manage with probability p and don't manage with probability 1 minus p. Right? And in that language, we can think of this event x equal to 1 as some event a which corresponds to success in our trial, or we can think of x equal to 0 correspondingly, which is a complement, as failure in our trial. Okay? That sort of language is what we are going to use. And you can think of some other ways of looking at this. You could think of this as being a coin flip, and success being heads, and failure being tails. Right? In each case, the P corresponds to the success or heads probability, and the other complementary probability of 1 minus P corresponds to failure.
Wouldn't it be P of x equals 1 equals P, and then P of x equals 0 equals
Oh, yes. Yes. Thank you. I'm very sorry. Getting ahead of myself there, or rather lagging behind. Those 1s and 0s are the values that the random variable takes. P and 1 minus P are the probabilities of those values. Thank you very much. Okay, so that sort of language is what we are going to use now to introduce some more classical random variables or distributions, and the binomial distribution is possibly the one that you're most familiar with if you studied probability at school. So binomial distribution, we can, as I've said, just write down the probability mass function and say that's what should give us a binomial distribution, and chances are you've seen it that way. So we have two parameters, n and p, and we say x is binomial with these two parameters n and p if we have the probability that x is equal to k equal to n choose k, p to the k into 1 minus p to the n minus k. And I'd like to insist that you specify what you want this to apply to. So you can write k from 0 up to n here, because implicit in these definitions is that we put 0 otherwise. Right, so even if we don't always write 0 otherwise, it matters to be precise, so at least we should specify the values for which we want this to be positive as opposed to 0. Okay, so that's our binomial distribution. And how does this arise? Well, that's where I'd like to refer back to events at this stage. And we can think of these events as heads and tails in coin tosses or successes and failures in Bernoulli trials. And so let us put that framework down. Suppose that A1 up to AN are events, and those events are independent with probability P. So probability of each of the AI is equal to P. And independence means that lots of probabilities of intersections equal to products of probabilities. Then the consequence is here, if we have this for all I between 1 and n, then the total number of well, let me first get the interpretation down. Although I've done it for a single one, it will be better to say we interpret AI as success in the ith Bernoulli trial in a sequence of Bernoulli trials, and then the number of successes, so number x of successes satisfies that x is binomially distributed with parameters n and p. Okay, why is this? Well, let's check. So we can calculate probabilities such as the probability of A1 intersection, etc., intersection AK to get k successes, intersection AK plus 1 complement, intersection up to AN complement to get no more than k successes. And note that by independence, this probability of intersections is a product of probabilities. Those products of probabilities are all p's and the complementary 1 minus p's. K of the p's multiplied into n minus k of the failures. That gives us the kind of event that contributes to seeing a total of k successes. But there are n choose k orders of successes failures, because they don't have to be successes first, failures afterwards. So and those make up the event x equal to k, and they all have the same probability, and that gives us the formula that we wrote down. Okay, this is the binomial distribution. So here's another, the geometric distribution. So the geometric distribution is arising similarly. Now we have a whole sequence of Bernoulli trials, but let's first write down what we mean by x twiggles geom of p. In that case, we say the probability that x is equal to little k is 1 minus p to the k minus 1 into p for k greater than or equal to 1, natural numbers, k greater than or equal to 1. Okay, and then the question of how this arises, we can say, suppose ai in f I greater than or equal to 1 are all independent with probability of each of the ai being equal to p. Again, we think of success in the ith Bernoulli trial, and I claim the number x here of trials before, no, needed up to and including, so let's just say needed until the first success satisfies that x is geometrically distributed with parameter p. Okay, and the check is simpler here. So if you work out what the probability is of x equal to k, there is now only one way in which you can require k trials until you see a success, because the first k minus 1 trials have to be failures, so events ai complement happen, and the kth one has to be a success. So you are multiplying by independence here, again, k minus 1 factors of 1 minus p into 1 factor of p. And in both cases, I should be precise and add by independence into my argument, because that is where my independence assumption came in. So let me write this explicitly. Okay, so this is the main geometric distribution. Sometimes you find a different geometric distribution. So note, sometimes the number, in the same context, the number of failures, and let's call it y, sorry, the number y of failures is also referred to as a geometric distribution. But that's not the same distribution, because if you don't count the final success, then of course you have one fewer in y as opposed to x, and so so then the probability that y is equal to k in this case would be 1 minus p to the k, because k failures is what you need to count before the first success, and then k is for k greater than or equal to 0. Okay, and that again makes my point where I say you should really specify for what values the formula you're writing down is satisfied, because otherwise it's really ambiguous, and you have to kind of, as a reader, think from the context, what is the meaning here for it to make sense. because in these examples, having derived them in this way, there's no doubt. But if I just were to write down a probability mass function and say this is a probability mass function, I mean, at some point, somebody needs to check that that really is a probability mass function, i.e. that satisfies these two conditions of being non-negative and summing to 1 as you sum over all possible values. And that, of course, involves knowing what values of k you put into the formula in order to get a probability that you want to be summing. Okay? Sorry? Could 0 be excluded? Where?
In the definition, from 0 to 1.
Where did I say from 0 to 1?
The geometric distribution, form P in the middle, from 0 to 1.
Should 0 be excluded? Well, that's a sort of philosophical question. I don't have to exclude it, because if I have no... Is it the other way? It's the other way. I want to exclude 0, because if I never see a success, then I won't be able to define a probability mass function this way. On the other hand, I can include 1, because if the probability of success is 1, then all I'm defining here is a boring distribution that puts all probability mass onto 1. Thank you. Yes, that is a mistake. Whereas for the binomial distribution, there's no such problem. I'm also defining some rather boring distributions for p equal to 0 and p equal to 1, but it is mathematically meaningful. Yeah, thank you for pointing that out. Okay, well, a few more distributions now without as much context, relying more on what I've said about being able to produce a sample space on which you can define a probability function and a function such that you have an instance of this distribution. So this is the uniform distribution on a finite set. And let's give the elements names. Let's call them x1 up to xn, although often they are integers as before, but they don't have to be. Let's insist there are n greater than or equal to 1 elements. Then it makes sense to say this is uniformly distributed if the probability for x to equal any one of them is the same, and therefore 1 over n for I from 1 up to n. Okay, and one more, number 5, the Poisson distribution. We say for a parameter lambda that is positive real here, x has the Poisson distribution with parameter lambda if the probability that x equals k is equal to lambda to the k divided by k factorial into e to the minus lambda for k 0, 1, 2, etc. Natural numbers greater than or equal to 0 is allowed here. Okay, and then as I haven't given a way in which they arise, here is an exercise for you. Check that these are probability mass functions. These well, I didn't call them Q here, but these probability x equals k that I can define as Q of x equal to k, that those actually specify probability mass functions. Okay, now in order to do that, particularly if you want to go directly into the geometric distribution or into the Poisson distribution, you will have to sum over infinitely many integers here. So the notion of a series is something that's being formally developed in the analysis course, for those of you doing the analysis course. But for the purposes of this course, we can't rely on that theory, and all you need for this course is what you find in the appendix to the lecture notes. So please refer there. In particular, you'll find you're given the geometric series, or the infinite sum of the geometric progression, as you may have called it, and you will also find the exponential series, or Maclaurin series, as you may have called it at school, and they are what you need in order to check that these Q's actually sum up to 1 in the cases of geometric and Poisson distributions. Okay, so what can we do with random variables? Let's get started on the notion of expectation. Random variables produce, as we like to think, random numbers, and we may want to know how big is a random number on average. So here, let's just go straight in with the definition. Whenever I have a random variable, I can consider defining the expectation, or also referred to as mean, of the random variable, and let's be precise, of a discrete random variable. Did I introduce that notation r dot v dot? Maybe I didn't, but maybe I should, because I'm not going to write random variable all the time. So let me say here, I want to abbreviate random variable as r dot v dot. So a discrete random variable is given here, and we define its expectation is defined by, well, let's just hope this makes sense for a start, and then I'll put a constraint on as needed. So expectation of x is a sum over all possible values in the image of x, and then we are summing the little x's, each multiplied into the probability that x is equal to little x. So what are we doing? Well, if we have a uniform distribution where these are all equal to the number of elements that we are summing, then we are just calculating the straight average of those possible values. But in more interesting cases where these are not all equal, these probabilities, we can look at this as a weighted average, because they still sum to 1, but some of the values are more likely. They get more weight when we are taking the average of all of those possible values, little x. Right? So that's our intuition for why this is in some way the mean of what we expect from our random variable. Now, I said let's write it, but then think, because some series, and this may be a series in cases where we have infinitely many possible values, some series converge and others don't. And so there is a genuine risk here that the possible values are so large that by multiplying the possible values into those probabilities, the sum is no longer finite. The sum is finite if I don't have the x in here, because it's a probability mass function that sums to 1. But with the x's, that may just trip over into this series, no longer being well defined. So what I need to write is, provided that this series is meaningful, for this series to be meaningful, well, there's some theory that we won't explore in this course, but that you will explore in the analysis course if you're doing analysis, and that condition is easy enough to state here. So I just put absolute values around my little x's, and then I can make sense of this quantity, this sum of all of those non-negative values. The worst that can happen is that this is infinite, and I only want to define my mean if this is finite. Okay, so that's the condition under which the expectation is well defined. And then we should just add if the series of those absolute values of x multiplied into probability x equal to x is infinite, we say the expectation does not exist. Right? Or in some cases, we can actually say that if all the x's are non-negative anyway, then we might as well assign the value infinity to those sums that don't converge. But that is not something that we should worry about first at this stage. So let's only look at expectations when they exist for the time being. And let's look at some examples. So first example, if x is uniform on the set 1, 2, 3, 4, 5, 6. So rolling a fair die is the setting here. Then the expectation of x that you get is, by definition, the sum k from 1 up to 6 of k into the probability that x is equal to k, which in this case is the sum k from 1 up to 6 of k into 1/6. And, well, you can do that sum, and you find 7/2. And, well, that should conform to the intuition that, on average, when you're rolling a die, you're getting 3.5, because that's kind of the middle value between the middle values 3 and 4, if you like, of the possible outcomes of your fair die. Okay, second example, if x is Bernoulli distributed with parameter p, what have we defined? We've defined the expectation of this Bernoulli random variable to be 0 times the probability of 0 plus 1 times the probability of 1, and that's p. P is the parameter of the Bernoulli distribution. And that is kind of often how distributions are parameterized. The mean is an important feature often. Now here is one distribution where things don't go so nicely. So it's slightly more artificial. If we suppose, as in some other examples that we've had, that the possible values of our random variable are the natural numbers 1, 2, 3, etc., and that the probability mass function that I want to consider here is 1 on n into n plus 1 for the value n to be the one that the random variable takes. So if that's my definition, then you may first want to check that this specifies a probability function. So px greater than or equal to 0 is OK, but the sum of those px of n for n from 1 up to infinity, is that equal to 1? Well, in fact, if you are taking the finite sum up to capital N of those px of n's, it turns out you get 1 divided by n plus 1, 1 over n plus 1, 1 minus 1 over n plus 1, and that does tend to 1. And so this is the meaning that we have a series that sums to 1 in this case. Now, have you seen this before? If you haven't, you can prove this statement by induction. Induction on capital N, because little n is just a dummy variable here. So capital N is what we are inducting over. OK, so what's interesting about this example? In this example, we have a summable series, because 1 on n squared is kind of giving you a finite sum. But as we multiply, as the definition of the expectation does, as we multiply by n, this series fails to be summable. So if we now look at the expectation of this random variable, then that means we look at the sum n from 1 up to infinity of n into the probability x equals n. That gives us the sum n from 1 to infinity of 1 divided by n plus 1, because there's one n here and one in the denominator that I've cancelled, and that is infinite. So the expectation does not exist. Okay, so there's one more example that is worth you looking into. If we let x be Poisson lambda, then the expectation of x, you learn to play around a little bit with the sigma notation if you write this out, and what you retain is just that lambda is again the mean of this distribution, which is our parameter. But let me not go into this, because I'd quite like to kind of draw complete the circle of having independence for events that are used to derive the binomial and geometric distribution, where we've actually started off by saying, well, a Bernoulli trial is the random variable. And so what is a binomial distribution if we are counting the number of successes in a sequence of Bernoulli trials? Well, it should be the sum of those Bernoulli random variables. But if I'd started off by saying, let x1 up to xn be n independent Bernoulli trials, well, I didn't define that, because I only defined independence for events and not for random variables. And so what I'd like to do is I'd like to define independence, which we have up here for events. I'd like to define that for random variables as well. So independence of discrete random variables. Okay, so random variables are functions on a sample space, so it is perfectly valid for me to say I consider two random variables on the same sample space. Here are random variables x and y, and we want to say that they are independent if for all x, y in R, well, we can say the events that we would consider as the probability mass function of x, well, as defining the probability mass function of x, and correspondingly what we would be using to define the probability mass function of y, those events, if they are independent for all x. Okay, and in formulas, what this says is that the probability that x is equal to x and y is equal to y, well, what is that supposed to mean? Well, that's just supposed to mean the probability of the event of all omega in omega for which both x of omega is equal to little x and y of omega is little y. It's the probability of that event that has to factorize into the probabilities individually of the event x equals x and the event y equal to y. Okay, that's a natural definition of independence in the context of random variables. And on the problem sheet, one of the harder questions is to relate this to an alternative way of defining independence. So here's an alternative definition. So x and y are independent if for all a, I want to use a and b, maybe I don't. Maybe I use c and d subset of R, the probability that x is in C and y is in D is equal to the probability of x in C times the probability of y being in D. Okay, so alternative definition, of course, only makes sense if it is an equivalent definition, and that's the purpose of the problem sheet question. You are showing that if random variables are independent in the sense of the definition, well, that holds if and only if they satisfy this criterion of involving all the subsets of the real line. Okay. So what else? Independence for two random variables is on the board. Now let's look at independence of any collection of random variables. We just follow the lead that we have from our general definition of independence of events, and we say a collection xi I in I of discrete random variables is independent if for all j subset of I finite and for all xi in R for I in j, the probability of the intersection now as a grand intersection of events xi equal to little xi, that is, no, well, I need to be specific here. This is over I in j, and that is equal to the product I in j of the individual probabilities of each xi, capital Xi equaling the lowercase xi here. Right? So really combining the ideas of using the events xi equal to little xi as my events ai, and using the idea of going to finite subsets of our index set in order to specify the independence of a bigger family, bigger than two elements of events. Right. So that just leaves enough time to give an example here. So independence is here. So if I move over here, I can say, let's go back to our binomial distribution. And let's say we can now say let x1 up to xn be Bernoulli distributed with parameter p. And let's suppose that they are all independent in the sense that we've just defined. And let us look at the sum Sn of all of these xi's. So if they are trials, then xi is equal to 1 if the trial is successful. So if we are adding up all the ones, then we get the number of successes. So this Sn is the number of successes in our sequence of Bernoulli trials. So that quantity, I claim, is binomially distributed. But let me say for each of the n choose k arrangements x1 up to xn. These are now my little x's with x1 plus, etc., plus xn equal to little k. So for each choice of possible values, zeros and 1, that add up to k, we can work out what the probability is of x1 being equal to little x1 up to xn being equal to little xn. And using independence, we can write this as the product of probabilities that x1 is equal to little x1, all multiplied up until xn equal to little xn. And so now my choice of saying let's take values of little xi that add up to k means that in each choice that I have behind that constraint, I will always get k factors that are equal to p, because there are probabilities for one of the xi being equal to 1, and then n minus k factors that are equal to 1 minus p, because they correspond to probability of xi equal to 0. Okay, and so pulling the threads together, this is saying that the probability that Sn is equal to k, which is by P3, if you like, the probability of the union of all of those choices of xi. There were n choose k ways of choosing the positions for the ones. That gets multiplied into that always same probability, p to the k into 1 minus p to the n minus k, and that is the binomial probability mass function. Hence, this Sn is binomially distributed with parameters n and p. Okay, so that's kind of closing a circle of ideas of having examples where we can handle things in terms of events and in terms of random variables, Bernoulli random variables in the case of the binomial distribution. So I've got a few minutes, and I think what I should do in those is look a little bit at this idea of having several random variables on the same probability space. It's something that we can do, because if you're given a probability space, just take several functions on that probability space. That will always give you some family of random variables. But more generally, what is the distribution of several random variables? There's a notion of joint distribution. So joint distributions arise whenever you have two random variables, or more generally multiple random variables on the same probability space. So discrete random variables x and y on some omega f p in the sense of the definition of a discrete random variable. Well, whenever you have that, we can say, let's define the joint probability mass function of x and y, and that is in analogy to what we've defined for a single random variable, a function that now takes two values, one for x and one for y, and spits out a probability in 0, 1, and is defining that xy maps to the probability, well, let me say, use the notation here, little p sub x comma y of x and y is equal to the probability that both x is equal to x and y is equal to y, in the sense that I defined, well, it kind of disappears. So let me write it again, meaning the probability of the set of little omega in capital Omega for which both x of omega is equal to little x and y of omega is little y. Okay, curly bracket closed, and then the ordinary bracket closed. Right, that notion is the joint probability mass function, and then we can kind of note that as we sum, but how do we sum over all possible values? Well, we have to sum over all possible pairs. So, so we can sum over all x in the image of x and sum over all y in the image of y. If we do that and sum across all these probabilities for the pair xy to be taken, those probabilities add to 1. And you can introduce the notion of a joint probability mass function just by requiring non-negativity and this double sum to be equal to 1, much in the same way as we defined a probability mass function in the case of a single distribution of one variable, as it were. Right? So that is something that I'll continue with next time, because there is now more to say about how this impacts back onto the distribution of each x and y, and then those so-called marginal distributions are worth looking into a little bit more. And then in the context of independence, we'll have another example as well. So that will be continued on Friday.